So yeah, I'm going to talk about some recent work which was with Kartik and Nibesh, which is aimed at addressing what we see as like a significant gap in the literature. Specifically, that's the lack of formal methods for analyzing properties of a blockchain protocol, such as the maximum throughput that it can handle. Okay, so let me explain what I mean by that. So at the moment, if you're going to study a blockchain protocol, a protocol for SMR, there are basically three standard timing models. Right? There's the synchronous, the partially synchronous, and the asynchronous settings. Probably everyone knows what they are. If they don't, it doesn't really matter for this talk. Common to all of these models, though, is basically the fact that they're sort of indifferent to message sizes. Right? We don't really care about message sizes. So in particular, messages are allowed to be of unbounded size. So if you're in the synchronous setting, then a message of any size and at time t is going to be guaranteed to be delivered by t plus delta. Right? And there are good reasons for this simplification. Basically, we want to keep things nice and simple, obviously, but we want tidy models. And generally, if you're just analyzing basic properties such as consistency and liveness, maybe you can get away with this. But an immediate consequence of that simplification is that we don't really end up with any good way to talk about things like maximum throughput. Right? So if you're in the partially synchronous setting, according to the model, I can form a block with any number of transactions I like, right, send it at time t, and if we're after GST, then it'll arrive within t plus delta. Yeah? Okay, so we don't have good ways to look at maximum throughput. And it's also a problem when we consider what I'll call real-world latency. Right? So roughly speaking, by real-world latency, I mean like the time between the first point at which a transaction is received by a correct processor and the point at which it is then finalized by all correct processors. Yeah? So in the standard models, latency is just upper bounded by just counting the number of rounds of communication required. Yeah? So we have 10 rounds of communication required in the synchronous model, then latency is 10 delta. Right? So there's a clear understanding that this is a simplification. This is not realistic. Obviously, in reality, sending larger messages will take longer. So then we have this kind of slightly awkward dance, if you like, in which we also consider communication complexity. In other words, the number of bits required in order to finalize. Right? And that's fine, but then we have no sort of formal way to weigh these metrics. So if I have a protocol that has like lower round latency but higher complexity, what does that mean in terms of real-world latency? We don't know. Right? So for example, consider HotStuff. Maybe it has like a greater round latency but lower communication complexity than Tendermint, for example. Okay, so which actually has real lower latency? We don't know, right? According to the model. Okay, so this is all well understood. I'm not saying anything controversial here. It's all been brought to a head by recent research in which people are looking to develop protocols that really can deal with very high throughputs and that scale well, can deal with large n number of processors. So as I'm sure people are aware, right? So there's kind of more traditional protocols, which I'll call single sender protocols, protocols like PBFT, where you have a single designated, potentially rotating leader who's responsible for proposing blocks. There's a sort of understanding that, okay, if you've got a single leader, they might act as some sort of bottleneck. Right? Again, it doesn't show up in the models, but there's some kind of understanding this might be true. So there's been lots of research in what I'll call like multi-sender protocols, okay, in which lots of processes distribute lots of proposals in parallel. Okay, so for example, we've got lots of DAG-based protocols like DAG-Rider, Bullshark, Shoal, Cordial Miners, and then Autobahn that we heard about earlier on as well. Okay. Which you might call a DAG-based protocol or not, but anyway, it's of that sort of flavor. Okay, so the problem there, okay, so people are interested in these protocols, there's lots of interest in them, but we have no way of formalizing, analyzing this claim, right, that their potentially better use of network bandwidth actually produces better results, better real-world latency, or maybe higher throughputs. Yeah. Okay, so that's the situation. Okay, so we're reluctant to introduce new models into distributed computing for good reason, because we don't want lots of the models all over the place, right? But okay, we're in a situation here where clearly some sort of new slightly more nuanced model is needed. Okay, so our goal in the paper, which is the same title as this talk, so it's the pipes model for latency and throughput analysis, is so first of all we want to describe a basic model which allows you to calculate latency as a function of network bandwidth, the number of processors, the incoming transaction rate, and other system parameters. Okay, well, so I'll describe it a little bit. It's a very simple model, really nothing much to it. With the model in place, it's then easily seen that each protocol has what we'll call a latency bottleneck. Okay, so this is an incoming transaction rate at which latency becomes unbounded over the protocol execution. Right? So maybe transactions just keep on building up and building up. Yeah? So in other words, a maximum throughput that the protocol could handle without unbounded latency. So the model allows us to calculate maximum throughput. Yeah, so we'll describe the model first of all, and then obviously our aim is, and this may be slightly harder actually because the model is quite simple, we want to use the model to analyze latency and maximum throughput for state-of-the-art protocols. So in particular, we're interested in asking questions, of the sort, are DAG protocols actually better? Or when are they better? And so on. Yeah, and obviously then we also want to run experiments, slightly annoyingly. I hope the experiments are going to be ready by this point, but then they're a few weeks off apparently, okay, so don't shout at me the experiments are there. The experiments are coming. Yeah. Okay, so in the rest of the talk, I'll describe it. It's quite a short talk, so I can't really do many details, but okay. I'll describe the model at a high level, and then we'll talk about results. So first of all, though, I want to sort of talk about some of the simplifications made by the model. There are lots of simplifications made by the model, all of which are maybe interesting to sort of dig into in more detail later on. Maybe you might want to complicate things. So first of all, we're going to focus on the good case, right? The message delivery is reliable and processes that correctly. There are at least two reasons for that. So first of all, real-world experience shows that the good case is actually the common case. If you look at data from real-world blockchains, you'll find that most of the time, most of the nodes are behaving correctly. Right? So that's really the case that you're going to care about most. Right? If one protocol has slightly better worst-case latency, but it's like 3 times slower, then generally speaking, you're probably not going to be interested in that protocol. Another consideration here is that perhaps surprisingly, using the new model makes latency analysis a bit more complicated. I mean, not that much, but it makes it a bit more complicated. So the idea is that by focusing on the good case scenario for latency, we can sort of highlight the results that people are probably most interested in, while keeping things at least reasonably simple. Okay. And then, so there are lots of other simplifications, but another one that I'll just point to right now. So we're not going to consider the time taken to carry out computationally expensive tasks such as signature generation, verification, and erasure coding. Okay, it would be easy to add these things in, and I think we certainly want to do that in the future. But the idea is we're going to produce the simplest model first of all, and take one step at a time, basically. Okay. And in the paper we have a list of, sort of 8 simplifications, all of which might be interesting to look at, but I'll just mention those 2 for now. Okay, so let's describe the model at quite a high level. So first of all, everything's sort of standard initially. So we've got a system of n processors. We're going to imagine there's a channel between each processor, each pair of processors. Processors can be correct, or they could be faulty. We're going to focus on the case that people are behaving correctly. Okay, and then we're going to assume all communication happens in the form of information parcels, each of which is some fixed constant number of bits. Okay, basically for now you can just think of an information parcel as a single bit. Okay, there's nothing really interesting to be said there. Okay, and then message delays. So what I'm talking about here, if you like, is the delay to send a single bit. Okay, we're not yet thinking about how long it takes to send larger messages. Okay, so as standard, time is divided into discrete slots. And the message delay between any 2 processors is always delta time slots. Okay, so first of all, this is for a single information, for a single bit, if you like. It's worth pointing out here that this is a big simplification, right? So in reality, there'll be processors all over the world. There'll be different delays between different pairs of processors. Anyway, despite that fact that that's true, we're going to keep things simple for now, and we're going to have the delay will be delta between every pair of processors for now. Okay. Also worth pointing out that we'll be analyzing protocols that might function in partial synchrony or asynchrony, right, where this bound doesn't generally hold. But we're interested in analyzing the good case for now. Okay, you can extend the analysis later on. And then we want to deal with bandwidth. So intuitively, the idea is that each processor should have a bandwidth of S data parcels, if you like, or bits per time slot. It's capable of uploading S parcels and downloading S parcels in each time slot. So how do we formalize that? So we're going to give each processor a single upload buffer and a single download buffer. Okay, so that's really a single buffer per processor. It's not per channel or anything like that. Right? So a single buffer per upload buffer, single download buffer per processor. And you just think of these as being sort of queues, right, in terms of stuff that you want to upload and download. So when a processor executes an instruction to send a message along any of its channels at time slot t, the corresponding parcels are immediately added to this queue, to its upload buffer. Each parcel added to the upload buffer has an intended recipient. Okay, and then at the end of time slot t, S parcels are removed from the upload buffer in a first in, first out fashion, and they then appear on the download buffers of their intended recipients at t plus delta. Okay. Obviously, you're just removing whatever's there. There's less there, you just remove whatever is there. And then at the beginning of a time slot, up to S parcels are removed from the download buffer in a first-in, first-out manner. And those parcels are then received by the processor, together with information specifying the sender of each parcel. Okay, so there's nothing surprising there happening. I think it's just very, very simple. We just have these two queues. Okay. Now we have to think a little bit, though, about so how fast are transactions arriving and where are they arriving. Okay, so what we're going to do, we're going to suppose that the set of processors as a whole, Pn up to Pn, they're always going to be receiving transactions at a total combined rate of D parcels, or bits, if you like, per time slot. Okay. So that's the set of processors as a whole. Now, though, there are some little sort of, potential complications, right? So the idea is with DAG-based protocols, everybody's supposed to be producing their own blocks. Yeah, and there could be complications there, so maybe there will be some duplication of transactions between different blocks. Maybe some blocks will contain transactions that are incompatible with other transactions and so on. Okay, so there are lots of considerations there that are worth going into. For now, we're going to sweep all of that under the rug, right? And we sort of imagine that basically, when we're considering what I'll call the multi-sender setting, when we're analyzing DAG-based protocols, I'm just going to imagine that the D parcels per time slot are just evenly divided between the end processors. Okay, so they get to D over N each, okay, somehow. Okay, so okay, so we have these two different settings. So in the single sender setting, which we're using for analyzing your standard sort of protocols like PBFT, I can suppose there's a designated leader that's receiving D transaction parcels at each time slot. In the multi-sender setting, we suppose that each processor receives D over N transaction parcels at each time slot. Okay, so now let's talk about some results then. So obviously the ultimate aim is we want to be able to establish results for SMR protocols. In order to do that, we kind of have to build up a little bit, basically because a lot of the standard DAG-based protocols use some simpler primitives just for the process of block propagation. Right? They might use consistent broadcast or reliable broadcast just for building the DAG in the first place. Okay? So we're going to build up. So first of all, I want us to focus on the single sender setting, and we'll just look at what I'll call a best effort broadcast, right? Basically just the task of sending blocks directly. Okay, so we're going to consider best effort broadcast, single sender setting. So here a designated leader, PL, receives D transaction parcels per time slot and sends those all to other processors. Our goal is to consider the rate at which PL can push data to all others in a context where data should be included in blocks that must also contain metadata. Okay, we're going to initially suppose that leaders sending data to others in a straightforward way without using techniques like erasure coding. Okay, so later on we'll come back and we'll talk about erasure coding. Okay, but for now we're not. Okay, so the analysis here is complicated slightly by the fact that turns out we have to consider sort of different forms of metadata. Okay, so we're going to distinguish between what I'll call dependent metadata. This is metadata such as PL's signature on the block, if you like, which can't be determined prior to knowing basically the full content of the block. Other than that data, okay? So you need to know everything that's in the block first before forming that part of the metadata. That's distinguished from independent metadata, which could be determined before maybe knowing everything else in the block. So for example, in some context, you might already know the previous block you're going to point to. Okay, so that would then be independent metadata. Okay, so some notation. I'm going to let M denote the total size of the metadata for each block. Well, the size of so MDE is going to be the size of the dependent metadata, and MIN will be the size of the independent metadata. Okay, so M is just MIN plus MDE. Okay, so then you can prove a formal statement that goes, well, here's an informal version of a theorem. So, yeah, so first of all, consider the single sender setting. If the incoming transaction rate is D, then lowest possible latency you can achieve for best effort broadcast is given by this formula here. You're not required to sort of engage too deeply with this formula. Okay, but to remind you, so M here is the size of the total metadata, N is the number of processors, D is the incoming transaction rate, S is your bandwidth, MDE is the size of the dependent metadata. Anyway, you don't really have to engage with the formula. I'll sort of point out what's important about the formula. Basically, the point here is that so if ND is small, okay, then the delta term is going to dominate. Okay, but we get a latency bottleneck appearing as ND approaches S, right? Then the latency goes up towards infinity. Okay, so as D approaches S over N, you approach this latency bottleneck. Okay, there's a factor N there, right? Okay. What happens in the multi-sender setting is that you get a similar sort of result, except that now the latency bottleneck appears as S approaches D. So as D approaches S. Yeah? Okay, so the factor N is no longer there. Okay, so now let's explain what's happening in these graphs here. So in these graphs, you've got latency on the y-axis. We've got a fixed incoming transaction rate here, okay, and we're varying n on the x-axis. Actually, both of these have all the same input parameters. This is just a sort of zoomed-in version of this one. Okay, the red is the single-sender protocol, and the green is the multi-sender protocol. I'll explain the purple one a little bit. Okay, but yeah, so basically what you can see happens here is you get a graph that's kind of like the graphs we saw in Natasha's talk earlier on, where you have latency being sort of fairly stable for a while, but then in the single sender setting, as you approach a certain point, you reach a sort of latency bottleneck, right? And the latency spikes up. Okay. So yeah, the red is single sender, green is multi-sender. What's happening here? The latency here depends on exactly how you have to form your DAG, right? So for the multi-sender setting here, we're imagining that you're forming a DAG, but we're not being strict about how you form it. So imagine that each block has to have n pointers to previous blocks. You just point to whatever you see. In the purple one here, we're imagining you're doing what lots of protocols do, where you build your DAG in layers. Okay, so you have to wait for one layer to form, then you form the next layer, and obviously that impacts the latency. Okay, so main takeaway. There are actually lots of nuanced considerations there, which we go into in the paper, but for now, the main takeaway is basically the latency bottleneck is a factor n higher in a multi-sender case, okay, kind of as you might expect. So now, though, let's move on to reliable broadcast, where we'll see completely different things happening. Okay, so I'm going to assume everybody knows reliable broadcast. If you don't worry, because this will be a short bit of the talk. Okay, so for reliable broadcast, we can do a similar sort of analysis. We get these formulas out here. It doesn't really matter what they mean for now. The important point is that in the case of reliable broadcast, the factor n difference in the latency bottleneck disappears now. Okay. So now we have, it depends how you implement the protocol, but basically here we have a factor 2 difference in where the latency bottleneck appears. And actually you can get rid of that using pipelining if you want to. Okay. Another thing to point out here, yeah, so if metadata has to contain sort of n pointers to other blocks, you also get a cubic dependency on n here in the multi-sender setting. Okay. Yeah, okay, so the main takeaway there is that it's completely different, right? So the factor n difference disappears. Okay, so now let's move on to state-machine-replication. To begin with, though, I'm going to compare single-sender and multi-sender protocols without the use of erasure coding. Okay, so perhaps not surprisingly, erasure coding changes everything. Okay. I'm going to take Sailfish as a representative example of a certified DAG protocol. You could consider other ones. You'll get some fairly similar picture. And importantly, yeah, we're going to consider both consistent broadcast and reliable broadcast as the underlying primitive for block propagation. Because, well, as you maybe you're not surprised from the previous slide, I guess a lot of the papers consider reliable broadcast as your underlying primitive. Turns out that's not a very efficient way to do things here, so you get much better results if you use consistent broadcast as your underlying primitive, although that gives some weaker guarantees. Okay, so here I won't show you the formulas, here are just some plots that give the sort of picture. Okay, so what can we see here? So the red one is Tendermint, the green one is Sailfish with consistent broadcast, and that's one with the low latency here. The yellow one is Sailfish with reliable broadcast. Okay, you can see it's not doing very well over there. And the purple one is HotStuff. Okay, so first of all, Sailfish with consistent broadcast is outcompeting everybody else in this particular regime, basically because you have this factor n difference in where the latency bottleneck appears. Okay, we're not using erasure coding yet. Yeah. Okay, that's one thing to point out. Another thing to point out is that Tendermint is outperforming HotStuff, and that's actually that's true in all regimes here. Okay, and then lastly, let's look at what happens when we have erasure coding, and perhaps unsurprisingly, that things completely change. So here we have the red line is DispersedSimplex. Here we're varying n on the x-axis, and here we're varying the incoming transaction rate on the x-axis. Okay. So basically, what you see here is the DispersedSimplex, right, which is your single-sender protocol, but using erasure coding. It outcompetes Sailfish with consistent broadcast for quite a wide regime, but the advantage of Sailfish with consistent broadcast is it has a latency bottleneck, which is higher by a constant factor. Okay, so to summarize then, so for state-of-the-art SMR protocols, you end up with trade-offs. So if you compare single-centered protocols using pipelining, if you like, and erasure coding, such as DispersedSimplex with DAG-based protocols, such as Sailfish and Bullshark, so the former, right, the single-centered protocols have a lower latency for a wide range of throughputs. On the other hand, the benefit of the DAG-based protocols is that they have this higher latency bottleneck, right, by about to finish, don't mind yet, by a constant factor. On the other hand, the comparison with your standard single-centered protocols that aren't using erasure coding is a bit simpler, because there you really do have this factor n difference in the latency bottleneck. Okay, so I'll stop there. Thanks for listening.
Questions? I know it must be in the paper, so could you summarize how do you derive those latency formula? Did you use something like the good old queuing theory to do that?
The best thing to do, I'll be giving a talk at A16Z next week, and I'll go through an example of that one. So, yeah, it's not okay. It's obviously a bit more complicated than just counting the deltas like you did before, a number of rounds, but it's not that hard, right? I mean, there's a sort of you have to go through a bit of algebra and stuff, but it's yeah, okay.
A very simple question. The plots were all derived from the formula with specific values for the metadata size. And
yeah, that's right, yeah. Yeah, but I tried to make them sort of representative, right? So
Thanks for the talks. It's really interesting. So can you expand a little bit on what happens between best effort broadcast and reliable broadcast? Why is it so different? Because intuitively, it seems that the payload, you only send it at the beginning, and then you're only exchanging metadata. So why is it so different?
No, so the problem is if you're doing reliable broadcasts and you're doing the multi-sender setting, there's the first round, say you're doing all simultaneously. There's the first round in which you'll send your own block, but then there's the second round in which you have to echo everybody else's blocks. Right? So that. No. You have to, if you're really going to do full reliable broadcasts, then you have to echo the block, right, the actual content, to make sure that everybody has actually received the block. I mean, you can consider variance instead, something that's closer to consistent broadcast, if you like, and then you'll overcome this problem, right? But if you're really just doing something like Bracker's broadcast, then you're echoing the block, and then you'll have this very inefficient round where everybody's echoing everybody else's blocks. Yeah.
Okay.
Any more questions? Cool. Let's thank Andy again.